Hello, good morning, guys. So welcome to the last session of the course Intro to Statistics. I hope you like this course. The deadline for our coursework, which is this one, is 11 a.m. today. So you got exactly 1 hour. So if you haven't submitted, please do so. I will try to have all of them marked and scanned and email them to you either today or tomorrow. I cannot promise because as you know, I do all the marking. But anyway, I will try to have them either today or tomorrow. But in any case, you should hear something from me before Monday about your R coursework, okay? And for the exam is, as you know, the exam is gonna be on Wednesday next week, 25th of May. The exam will cover everything we've done except for the 2 sample confidence interval, 2 sample test of hypothesis, graphical analysis of data, normal approximation, continuity correction, and that's it, I guess, right? So everything other than those topics will be in the exam. And the style of the exam will be similar to the last 4 years exam papers. That's 2021, 2020, 2021, 2019, 2020, 2018, 2019 resit, and 2018, 2019. So I suggest for revising for the exam, you just focus on the last 4 exam papers, right? So today I'm just going to do some revision questions. If you guys could tell me like any particular questions from the past exam papers that I can do, I would appreciate it. Hello, guys. Is there like a particular question you want me to do from the past exam papers? Yes? No? I just started preparing. I guess, the stat methods is one of the first exams, I guess, for you guys. Intro to stats. So you better, if you haven't started preparing, you better start soon, right? A2. This one. Okay. So this is A2 exam. Exam 18-19. Is it 2018-19? So you have, I'm going to do part B. You have a random sample from an exponential distribution with parameter 1 over theta. You have theta hat equal to n times the minimum. So possible estimator for theta. And the first part is to derive the bias for theta hat, right? Remember, the bias is defined as the expectation of theta hat minus the parameter that you're trying to estimate, right? So this is the expectation of n times the minimum right? Now n is a constant, so you can put it outside. Okay. All right. Now, to find the expectation of this, first you need to figure out the distribution of the minimum of x1 to xn. Because you cannot take the expectation inside the minimum. That's not valid, right? So you need to first derive the distribution of the minimum of x1 to xn. So let me call, you don't need to call it z. You can call it any other name you like, okay? Like w or u or omega, or whatever you like, okay? Okay, now what I'm going to do is I'm going to derive the distribution of z. So I will start with the CDF. The CDF of z is going to be okay. Now this I'm going to write this as 1 minus. You will see in a minute why I'm doing this. I'm going to write this as 1 minus the probability that capital Z is greater than Z. Now I'm going to put the definition of Z, which is this. Into this, right? Now, if the minimum is greater than Z, then logically speaking, each of the x1 to xn has to be greater than Z, right? So this will be the 1 minus the probability that x1 is greater than Z up to xn is greater than Z. Right? Now, in the next line, I'm going to use, we are told that x1 to xn are independent random variables, right? So I'm going to use the independence and write this as right? Okay, guys. Now, each of x1 to xn, each of them have the same distribution. In this case, the exponential, right? Therefore, each of these probabilities are equal, right? They are the same. So you can write this as the probability that x1 is greater than z to the power n. You follow me? Because each of the probabilities is the same, right? Now, what you have here is the CDF of x1. We know that for the exponential distribution with parameter 1 over theta, the CDF, you should look it up, the CDF is okay. So the 1 here and the 1 here will cancel. So what you get is 1 minus nz divided by theta. All right. So this is the CDF of z. So the PDF of z is the derivative of this with respect to z, which is Okay. All right. This is the PDF of Z. Are you guys following me or what? Any questions? You all right? Yeah. Okay. Now what you see here is that this is what you see here is this is actually the PDF of an exponential distribution with parameter n by theta. Do you see that? What you see here is the probability density function of an exponential. You know the PDF of an exponential, right? It's like a times e to the power minus ax. So what you have here is the PDF of exponential with parameter n by theta, right? Okay, now let's go back to the beginning where we were here. We were here, right? We wanted to find the expectation of this, right? Now what we found out here is that the minimum has a distribution that is exponential with parameter n by theta, right? So going back to, let me put a box here. Let me put a box here so that, right, going back to this guy here, going back to this, all right, we can write from this, right, from this we can write that the bias of theta hat, right, is equal to n times the expectation of z minus theta, right? Now, we know that z is exponential with parameter n over theta. And one property of an exponential, you might know this, like you should go to, these are things you don't need to remember unless they are in the formula sheet. So if you go to this, one property of an not this one, sorry, I'm sorry. If you go to this link here, a property of an exponential distribution is that the expectation is 1 over lambda. You see this here? The expectation of a exponential variable is that is equal to 1 divided by lambda. So in this case, it will be theta by n. So this is 0. So what this means is that theta hat is unbiased. Is that clear, guys, or not? So we have shown that the estimator for theta hat, so the estimator for theta has bias equal to 0, right? And therefore it is unbiased, right? Some of you look lost. Are you guys okay or what? So we just done part one of part B of exam paper 2018-2019. You okay? All right, now to do the second part, which is part 2. Part 2 is asking you for the MSC of theta hat, which is the same as the variance of theta hat because the bias is 0. Okay? Now this is variance of n times z, where z denotes the minimum of x1 to xn, right? Now n is a constant, so you can pull it outside. Right? Now we know that z is an exponential variable with parameter n over theta. Now, returning to this, you see that the variance of an exponential is 1 over lambda squared, right? So this is going to be theta squared divided by n squared, right? Okay. So these two guys cancel out. So the MSC is equal to theta squared. You okay, guys? Yes? All right. So that's part 2. Part 3, well, we have already answered the question. So part 3, the answer is yes, because the bias is 0. For part 4, the answer is no, because the MSC does not approach 0. Actually, the MSC is a constant. The mean squared error is a constant in this case, so it cannot approach 0 as n approaches infinity. You see, for estimated to be consistent, its MSC must approach 0 as n approaches infinity. In this example, it does not, right? Okay. You guys okay? So we just did. So you just came in. We just did the question 8.2 from 2018-2019 exam paper. Any other questions you like me to do? I mean, there are lots of questions. Come on, guys.
Can you do B6 for the
Same exam paper? Yeah, okay. All right, let's see, B6. Whoa. Yeah, here we are. So this is all right. Part 1 is to write down the likelihood function for sigma squared. So remember, the likelihood function is because in this case you have a random sample x1 to xn, the likelihood function is going to be the product I from 1 to n right? Now, if you take the product of this, I can do this in multiple steps. I assume you know how to simplify products of functions. I think there's a video I did on it. There's a video let me show you where it is. Just try to learn this video if you haven't done it already. So this is the video on properties of products. So try to remember, these are the properties I would like you to know. I mean, this you should know anyway. This is not statistics. This is mathematics. You should know how to simplify products of functions, right? So if you do that, this is what you will get. You will get, I'm not going to explain, but I hope you know this stuff, because all right, this is what you will get. You should do the products of terms, right? I mean, over the years, I've seen many people having problems simplifying products of functions. I mean, it's not statistics, it's mathematics. So you should please brush up your math, right? Okay, you should have problems, okay? Right, so this is the likelihood function, right? So that's step 1. Step 2 is to show that the MLE is equal to this. So to find the MLE, you take the log of the likelihood function, which is minus 2n log sigma, plus the sum I from 1 to n of log of xi minus 1 over 2 sigma squared right? And then you differentiate this, you differentiate the log with respect to sigma squared. Well, it really doesn't matter whether you, okay, let's differentiate with respect to sigma, because the reason is that sigma, the mapping from sigma to sigma squared is a one-to-one function, sigma being positive. Remember, sigma denotes the standard deviation, so it cannot take negative values. So the mapping from sigma to sigma squared is a one-to-one function. All right, so it doesn't matter whether you differentiate with respect to sigma squared or sigma, it's the same, right? Okay, so you get minus 2n divided by sigma. Then the derivative of this is you set this to 0, and if you solve this, you get sigma squared equal to 1 over 2n okay. Now, to make sure that this is an MLE, you need to take the second order derivative. Sorry, this should be d here. D sigma squared, which is plus, by the way, 2n divided by sigma squared minus 3 divided by sigma to the power 4 times the sum of this, right? Now, to show that this is negative, because we only need to show that this is negative when sigma equal to sigma hat, right? Okay, so one way you can do this is to pull out plot this as a common factor. Then in brackets you have 2n sigma squared minus 3 times okay, right? Now I'm going to substitute sigma squared equal to sigma squared hat, right? Now if you do that, this guy here will become right? You follow me? You see what I've done? I have replaced sigma squared by sigma squared hat, which is this guy here. So if you replace this one by this one, you get this, right? You follow me or no? Yeah? And this is clearly negative, all right? So hence, all right? Any questions so far? You guys okay? All right, let's look at part 3, sorry, part 4. Oh, sorry, part 3. Part 3 is to deduce the maximum likelihood estimator for sigma. So, as I said a minute ago, right, the sigma to sigma squared is 1 to 1 function. It's a one-to-one function because sigma cannot be negative. Remember, sigma represents standard deviation, so you cannot take negative values. So you only have the positive real line to work with. So the function from sigma to sigma squared is one-to-one, right? So therefore, by do you remember the invariance principle? It's something that I talked about in the class. I will show you. If you don't remember, let me show you. Maybe you guys forgot. I don't know. Right. You should go under this. You see, this is one of the properties of MLE, that if G is a one-to-one function, and then G of theta hat is the MLE of G of theta, right? These are properties of MLEs that I talked about a while ago. You may recall that. So by the invariance principle, the MLE for sigma hat, right, is going to be the square root of the MLE for sigma squared. Yeah? Is that clear to you? So I'm using this invariance property. Okay? Right, now that's part 3. Now part 4 is to show that the estimator in part 2 is unbiased. All right, now, so this is part 4, and we have this estimator, which is, let me write it down one more time. So we want to show that this is unbiased. So we need to work with the bias of it. Right? This is the bias. Right? So this becomes the expectation of right? Take the expectation inside, you get all right, now how do we find this? To find the expectation of xi squared, basically you need to integrate the PDF, right? This is the PDF that's given to you, right? So can you tell me what the integral should be? It's going to be 0 to infinity because the PDF is defined only on the positive real line. Okay, 0 to infinity of x squared times the PDF, which is x over sigma squared, times exponential of right? Let me know if I'm doing it correctly or not, right? I hope I'm doing it right. So this will become 2. You should take the constant outside, is 2n sigma squared times the sum 0 to infinity of x cubed right? Now, how do you do this integration? Any ideas? I mean, integration is something you should have learned. You should know how to do from your calculus courses, right? So one way to do this integration is to do substitution, right? So let's set y equal to x squared by 2 sigma squared. So x will become square root of 2 times sigma times square root of y, right? So dx by dy will become sigma divided by square root of 2y. Okay, so let me put this in a box. Right? Okay, now I'm going to put this into the integrand, right? So you have 2n, 1 over 2n times 2n times sigma squared. Then you have sum 1 to n. Then you have 0 to infinity. X cubed will become cube, right? And this will be y to the power 3 over 2, then e to the power minus y, dx is sigma root 2 root y dy. Are you guys following me? Are you okay? Correct me if I'm making any silly mistakes, let me know. Right? Right? So this is what you get. It's just, I mean, you should have a lot of experience with integration. There will be quite a few integrals in the exam next week. So just try to practice your calculus. Right? Okay. Try to practice your calculus. Okay, it's nothing to do with statistics, really. Okay. Anyway, so if you divide this by this, you get, there will be a 2 coming outside, and there's a sigma cube coming outside, and then you have sum, sorry, I left out a sigma squared here. Then you have sum 0 to infinity of y e to the power minus y. There's a sigma here too, so actually this will be sigma to the power 4. Sigma to the power 4 dy minus sigma squared. Right? Are you following me? All right, are you guys with me or what? All right, so the 2 and the 2 will cancel. The sigma squared will go with the sigma to the power 4. You have sigma squared divided by n, then 1 to the n. This guy here, does this ring a bell to you guys? What is this? This is known as this is the gamma function at 2. Right, minus sigma squared. You remember what the gamma function is. It's one of the formulas you need to remember for the exam. Let me show you. Let me show you where it is. The gamma function is this one here, right? This is the definition of the gamma function. All right? So using this, you can write this integral as gamma function at 2, right? And gamma function at 2, according to this property, gamma function at 2 is 1 factorial, and 1 factorial is 1, right? So this guy is equal to 1, right? So what you have is sigma squared times divided by n, and the sum of 1 is n minus sigma squared, which is 0, right? And hence, all right, is that clear to you all? I mean, it looks like a lot of integration, but it should be straightforward for you guys. I mean, given the amount of calculus you have done, Yeah, it shouldn't be hard for you guys. So that's part 4 of question B6. Now part 5 is similar. Do you want me to do part 5 or can you do it by yourself? Part 5 is similar except that you need to find the MSC. So you need to find the MSC of the estimator and show that it approaches 0 as n approaches infinity. Can you do that by yourself or you want me to do it? All right, any other questions you want me to do in the exam paper? Just tell me. Which are the exam questions you want me to do? B5. Huh? B5. Is it the same exam paper? Yeah. Oh, B5. Oh, this one, yeah. So this is question B5, 2018-2019 exam. Right. So you have x1, x2 exponential, and you have theta 1 hat. You have theta 1 hat defined as a times x1 plus x2, and you have theta 2 hat defined as b times the square root of x1, x2. Right. Now, part 1, show that a equals to half if theta 1 hat is an unbiased estimator for lambda. So, right, so we need to find the bias of theta 1 hat, which is the expectation of theta, which is the expectation of this minus lambda, because remember we are trying to estimate lambda, right? So this is going to be the expectation of a times x1 plus x2. Yeah, a is a constant, so you can pull it outside. So this becomes right. Now we know that x1 and x2 are exponential variables with parameter 1 over lambda. So their expectation is going to be lambda plus lambda. You see, that's one of the things I showed you earlier. Hope you're, I mean, not showed you, is you should go to the common probability distribution and look under exponential. You see that the expectation is this, if the parameter is lambda. So in this case, the parameter is 1 over lambda, so the expectation is lambda, right? So what you have is 2a lambda minus lambda, which is 2a minus 1 times lambda, and this is 0 if a is equal to half. So the estimated theta 1 hat is unbiased if a is equal to half, right? That's part 1. Part 2, are you guys following me? Or let me give a shout if you're not following me. Part 2 is to do with the bias of theta 2 hat. The bias of theta 2 hat is the expectation of theta 2 hat minus lambda, which is the expectation of right. We are told that x1 and x2 are independent random variables, right? Which means that b is a constant. You can take it outside. You you can write this as you can write it like this. That's because of independence, right? Now, and we also know that x1 and x2 have the same distribution, right? They both of them, they have exponential with parameter 1 over lambda. So you can write this as, right? These two are the same, right? Like this. Now, to find the expectation of the square root of x1, you need to do integration. So you need to basically square root of x times the PDF of exponential with parameter 1 over lambda like this. Do you see what I've done? This is the PDF of the exponential, and this is, you're trying to find the expectation of the square root of x, right? So to do this integration, once again, you need a substitution. So I'm going to set y equal to x by lambda. So this implies that x is equal to lambda y, and this implies that dx equal to lambda dy. Okay. Now subbing this into the integrand, you get b in brackets 0 to infinity. Root of x will become like this, right? Are you following me, guys, or not? The lambda, this lambda and this lambda will cancel out. The root of lambda, you can take it outside, so this becomes all right. All right. Now, once again, I'm going to use the definition of a gamma function. Now, this guy here, you should go back to the definition of gamma function, right, which is this one on the screen. This will be gamma function at 3 by 2. All right, so this will be b. Now, gamma function at 3 by 2 is half times the gamma function at half, right? I mean, you don't need to know this for the exam, but this is a property I think I mentioned in one of my videos. You should go back to the website. You will see there's a video about the gamma function. You see, so I'm using the property that gamma at a plus 1 is a times gamma at a, and gamma at half is root of pi. Okay, so this will become, if you take the square of this, this will be b lambda pi divided by 4 minus lambda, right? And this is 0 if and only if b is equal to 4 divided by lambda, right? So I think that's the answer. Is that right? Yeah, 4 divided by lambda. 4 divided by pi, 4 divided by pi. Yeah, 4 divided by pi. All right, is that clear, guys, or no? Sorry. Yeah? So that's part 2 of B5. Part 3 is easy. Part 3 is, so to do part 3, you just need the variance of theta 1 hat, which is the variance of a times x1 plus x2, right? So you take the a outside, it becomes a squared, in brackets, variance of x1 plus the variance of x2. All right. Now x1 and x2 are exponential variables, so this will be lambda squared plus lambda squared, right? And so this is 2a squared lambda squared. So that's part 3. And part 4 is to find the variance of theta 2 hat. That's also easy because you can write this as the expectation of, I'm going to use a different formula with a purpose. I will show you why. See, I'm going to use this formula. I will explain why I'm doing this. Right? Because when you remember, theta 2 hat is defined as b times the square root of x1, x2. Right? So if I use this formula, right, and take the square of theta 2 hat, right, this will become expectation of b squared x1, x2, right? And this we already know is equal to, we know this is already lambda, because we showed earlier that, we showed in the previous part, was part 2, that the expectation of theta 2 hat is equal to lambda if b is equal to 4 over pi, right? So this will be 4 over pi squared. Now x1 and x2 are independent variables, so you can write it as like this, right? Minus lambda squared, right? So this will be 4 over pi squared sorry, let me write it, 4 divided by pi squared outside, not here. The expectation of x1 is lambda, the expectation of x2 is lambda. So the answer will be 4 divided by pi squared minus 1 in brackets and lambda squared outside, right? So that completes part 4, and part 5, I'm sure you can do it by yourself. All right, so that B5, are you guys okay with this? Yes? All right, and some other questions, please. So this is, I've done 3 questions, 3 exam questions. I know the typed solutions are not always detailed enough, so if you want more details, just contact me. I'll get you more details, right? So is there some other question you'd like me to do today? I don't know, I'm not sure if I have the time, but A4C. Part 2. All right, yeah. I think the trick here, all right, in the short time I have left, I've already run out of time, guys, but what you need to do in this case is to, you see, you are given the CDF of Z. Just bear with me for a second, guys. I know I'm running out of time, but to answer this question, you need to set this equal to alpha by 2, right? And solve for Z. So if you set this equal to alpha by 2 and solve for Z, you will get, correct me if I'm wrong, you will get 1 minus alpha by 2 log and then you get theta minus. This is what you will get for z if, correct me if I'm wrong. And also you need to do the same thing by setting, you need to set the same thing by setting the CDF equal to 1 minus alpha by 2. And this will give you something like, correct me if I'm wrong, this will give you something like this. All right? So using these two statements, you can say that the probability the probability of z lying between this and this, right, is 1 minus alpha. Right? And then rearrange the statement. Rearrange in terms of theta, right? And that will give you the confidence interval for part 2. This is part 2 of question A4, right? Is that clear? So what you need to do is you need to set the CDF equal to alpha by 2 and solve for z. Hopefully this is correct. I did it out of my, and just check my calculations. And the same thing, set this equal to 1 minus alpha by 2 and solve for z. You may get something like this. And then from these two, you can argue that the probability of this is 1 minus alpha. And then rearrange this inequality as a subject on theta. That will give you the confidence interval. All right, guys. So it's been a pleasure teaching you. And for any questions about the exam, just feel free to contact me 24/7 by email, Skype, Zoom, or phone. I'm also in my office until 6 p.m. every day, so any questions, just feel free to drop by. No need to make an appointment. All right, so best of luck with everything. All right, guys? Okay.
Teacher, how do you know the square root of x also follows the exponential distribution?
Yeah, x1 follows the exponential.
But this is square root of x.
Yeah, I know it's square root of x. So the question here is to find the expectation of the square root of x.
Yeah.
Right? So I'm using the fact that x1 follows the exponential. X1 follows the exponential to find the square root of x. You can, I mean, I'm not arguing. I don't know the distribution of x1, sir. I don't know the distribution of x1. Right? All I'm assuming here is that x1 has the exponential.
Yeah.
Not square root of x.
Yeah.
So I'm using that to find the expectation of square root of x1, which is this. And it turns out to be this.
And because the x1 and x2 follows the same distribution, so they can...
Yeah, they're the same, yeah.
Okay.
Yeah, they're the same. Yeah. Yes. You guys?
Do we get a formula sheet in the exam?
Yeah, no formula sheet. You need to remember the formulas in this sheet. Yeah.
So, you know if you go back to the main page for stats,
Yeah.
it says
This one.
yeah, that one. Do you not get?
Yeah, I think you may get this. Yeah, you'll probably get it in the exam, the tables, because that contains the tables for the normal and the t and the chi-squared, which you may need to use in the exam. Memorize what? The tables?
There's some distributions in there as well.
It has the
Yeah.
a
few distributions. Yeah. But the only distributions you need to memorize are the ones in the sheet.